Okay, so last time we looked at the Metropolis Hastings algorithm as a way of constructing Markov chains that have a specific stationary distribution. Today I'm going to give you a brief overview introduction to Gibbs sampling, which is another way of constructing Markov chains that have a desired stationary distribution. So actually, Gibbs sampling turns out to be a special case of Metropolis Hastings, but that's not going to be obvious immediately, and it's probably not useful to think about it that way initially. But just to keep that in mind, it will turn out that Gibbs sampling is a special case. But for now, let's just take a look at the right up here, the introduction to Gibbs sampling. So the basic idea behind Gibbs sampling is to use conditional distributions to sample from a joint distribution. So let's see the very simple example here. So the example here is I've got two random variables, x and y. They're each binary, okay, and they have the following joint distribution as given in this table here. So the probability that they're both 0 is 0.6. The probability that they're both 1 is 0.15, and the probabilities that x is 0 and y is 1 is 0.1, etc. So that's their joint distribution. And what we're going to do here is just compute the conditionals based on. We're going to start off by computing the conditionals based on that joint distribution. So what do I mean by the conditionals? I mean, what's the conditional probability of x being 0 or 1 given, say, y is 0, or of course given y is 1. There are only two possibilities. So given that y is 0, x is either 0 or 1, and standard simple application of Bayes' theorem tells us that the two probabilities are 0.8 and 0.2. So given this is just Bayes' theorem here, we just apply Bayes' theorem and we compute the conditional probability that x is 0 or x is 1 given y equals 0. So that's these two probabilities here. Okay. And the same way we can compute the conditional probabilities of x given y is 1. And of course, we can also compute the conditional probabilities distribution of y given x. So again, this is just simply applying Bayes' theorem to compute the probability that y is 0 or 1 given that x is 0, and the probability that y is 0 or 1 given x is 1. Okay, so just to say that again, here are the joint, we're given this joint distribution for x and y, and here we've computed the conditionals. And here's the question. What if we start at some value of x and y and just iterate the following steps? First, we're going to simulate a new value of x from its conditional distribution given the current value of y. And then, second, simulate a new value of y from its conditional distribution given the current value of x, the one we generated in the first step. And then we go back to generate a new value of x given the current value of y from its conditional distribution, and repeat. We just keep going up like that. So you might visually think about it in terms of we're going to generate some x1 and y1. We're going to have to initialize somehow, and then we're going to generate x2, but it's going to be from the conditional distribution of x given y1 or y equals y1. So so actually that depends on what y1. And then we're going to generate y2 using the conditional distribution of y given x equals x2. So actually the dependency is kind of like this in terms of the way we're going to generate these. Sorry, that should have been a y. Etc. And just to think about how this is a Markov chain, think of it as a the state space as being the pair. So this is, you know, the first state of the Markov chain, and then the second state of the Markov chain. So each pair think of that as a location in the space 0, 1 cross 0, 1. So the possible, you know, so the possible values of the Markov chain are 0, 0, 0, 1, 1, 0, 1, 1. Yeah, it's a Markov chain on that state space, and you could, you know, if you wanted to, we're not going to do this, but if you wanted to, you could write down the transition probabilities. If, you know, if x1 and y1 are 0, 0, what's the probability that x2 and y2 are going to be 0, 0, and put that there, etc. Okay, so you can see it's Markov. In fact, x2 and y2 don't even depend on x1; they only depend on y1. But in general, you know, xn and yn depend on the past only through xn minus 1 and yn minus 1. Right? They satisfy the Markov property. In fact, they only depend on yn minus 1, but that's, you know, that's a stronger condition. Okay, so this, given this state, you can generate this state. And in fact, you only need to know y3, but still, it still satisfies the Markov property. So this is a Markov chain. Oh, sorry. So this is a Markov chain. And so here's what happens if we generate samples from that Markov chain. So this is code to do that. So we have this function here, sample x given y, which just if y is 0, you get a Bernoulli 2, and if y is 1, you get a Bernoulli 0.6. That just comes from these numbers up here. If y is 0, then it's Bernoulli 0.2. That's what these say. And if y is 1, then you get what x is Bernoulli 0.6. That's what these numbers say. So that's where these conditional distributions come from. And the same for these. And then all that's going on here is we're setting up a vector of x and y's to save our results. And we're starting, in this case, we start from 1, 1. And then we just sample x given y, and then sample y given x. So each time xi is being sampled from its conditional distribution of x given y is the value at y, the previous iteration. That's yi minus 1. And then y is sampled from its conditional distribution given the current value of x, which is xi. Okay, we just iterate those processes. So here's what it looks like. So we started, at least for my random realization, we started at 1, 1, and we generated an x and then a y, and we got a 1, 1 again, and then we generated an x and a y, and we got 1, 1 again. And, you know, as you can see, each iteration, sometimes you move, sometimes you don't. So what if we summarize the long run proportion of times that we saw a 1, 1 versus a 0, 0 versus a 1, 0, or presumably some 0, 1s as well? Here's what we get. So it was 1,000 iterations. So out of those 1,000 iterations, 617 were 0, 0, 137 were 1, 1. These were the proportions of the others. So what if you look at these numbers, what you can see is they're actually pretty close to this joint distribution that we started with. And that's not a coincidence. So look, 0.6 and 0.15 are the numbers on the diagonal. And in those 1,000 iterations, we actually got something like 0.62 and 0.14. So pretty close to 0.6 and 0.15. And these are also close to 0.1 and 0.15. So what you can see here is that that's putting it in mathematical terms, the stationary distribution of this Markov chain is actually the joint distribution P of x and y. But we generated the Markov chain using only the conditionals. So if I hadn't have told you the joint, if I'd only told you the conditionals, you could have still kind of coded up this Markov chain and you would have been able to work out the joint from effectively work out the joint from the conditionals by running a Markov chain. Okay, so what's the explanation? Why does this happen? Why is it the case that when we iteratively generate x from its conditional given y and y from its conditional given x, and we repeat that, why does the Markov chain that we define in that way have the joint distribution of x and y as its stationary distribution? Well, essentially, the way to think about that is imagine, remember what stationary distribution means. Stationary distribution means that if we start there, if we generate an x and a y from that stationary distribution for, say, x1 and y1, then the distribution of x2 and y2 will also be from the stationary distribution. That's what stationary distribution means. So if you start there, you stay there. Once you get there, you stay there. Okay, and if you, it's kind of, it's basically just slightly messy algebra, but if x1 and y1 are from the joint, if we generate x1 and y1 from their joint distribution, then in particular, y1 is from its marginal distribution. That's what marginal means. If you generate x and y from their joint distribution, then y comes from its marginal distribution. Right, so y1 comes from its marginal distribution. So if we then generate x2 using the conditional distribution of x given y, like this, we know that y came from its marginal, so the joint distribution of x2 and y1 is just the marginal for y times the conditional that x2 equals x given y, which is the conditional of x given y. That's this distribution, because that's what we used. And when we multiply this by this, we get the joint again. So what this says is that if x1 and y1 are from their joint, then x2 and y1 are also from the same joint. And then you can do the same argument again to show that if you now generate y2 from the conditional given x, the value of x2, then y2 and x2 will also be from the joint distribution. So in other words, if x1 and y1 come from the joint distribution pxy, then so do x2 and y2 come from the joint distribution pxy. And that's exactly what stationary distribution means. So if we start by sampling from that, we will stay there. Of course, we didn't start by sampling from that. We just started from 1, 1, but that doesn't matter. This argument shows that that joint distribution is the stationary distribution of this Markov chain. That's this joint distribution here up the top is the stationary distribution for this Markov chain, because we used the we used the conditionals computed from this joint as our updates. Okay. And that's the basic idea behind Gibbs sampling, is that in general, to generate a Markov chain with, say, stationary distribution. Okay, let's put it in Bayesian terms. Imagine that we're trying to generate from a conditional distribution of a bunch of parameters, thetas. So that's a parameter vector. So in the, I don't know, maybe it's a bunch of well, it's a bunch of parameters. Maybe it's a bunch of means of normal distributions in a mixture of normals, as an example. Given the observed data D, let's say, we repeat. Okay. I'm going to omit the initialization step. We're going to generate theta 1 from its conditional distribution P of theta 1 given theta 2 up to theta P and D. And then generate theta 2 from P of theta 2 given theta 1 up to theta P without theta 2, of course, and D, etc. So actually this is sometimes written, it's a convenient notation to write this theta minus 2, just means all the thetas except theta 2. So I'm using that to mean all those thetas there and D. And in general, so the last one will be theta, there'll be a dot, 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 generate theta P from P of theta P given theta minus P and D, okay? So what I've done here is generalize from X and Y, which is just 2 random variables, to P random variables, theta 1 up to theta P. And I'm just sampling from the conditional distribution of one of them, given all the others. And there's a D occurring in every case, but that's just because we usually in Bayesian inference want to do inference given D. And so D just occurs everywhere here in all these conditionals. And so just by exactly the same arguments, essentially, this will have stationary distribution is this joint distribution here that we wanted to sample from. Okay, so the case we've just given was where there's no data, the no data case, so D is kind of empty, and P is 2. Theta 1 was X and theta 2 was Y. Yeah, so but Gibbs sampling generalizes to more than just that two-dimensional case, and in fact, as we'll see later, you can group the variables however you want. So we could have, an alternative would be to generate theta 1 and theta 2 from P of theta 1 and theta 2 given all the other thetas. And then let's say theta 3 up to theta P from P of theta 1 up, theta 3 up to theta P given theta 1 and theta 2. And so this is called block Gibbs sampling. So the point here is that you can kind of group the thetas however you want. These thetas could be, put another way, each theta could be a vector. It doesn't have to be a scalar. You don't have to be using a univariate distribution at each step. You can be using a joint distribution. As long as at each step you're updating a subset of variables by sampling from their full conditional distribution given all the other variables. That's what's called a Gibbs step. It's where you sample from a subset of random variables from their full conditional distribution given all the other random variables. And if you iterate that kind of thing, eventually updating all the variables, then you've got yourself a Gibbs sampler. Okay, so that's the basic idea. Maybe that's the notation for, or the phrase full conditional. That just means their conditional distribution given everything else that you're not updating. That's what full conditional is. So that's a phrase you want to bear in mind. So you could ask, well, what's better, Gibbs sampling or Metropolis Hastings? And we'll come to that. The general answer is hard to say. But one advantage of Gibbs sampling over Metropolis Hastings is that you don't have to choose a Q, right? You don't have to choose a proposal distribution. And in particular, you don't have to choose a variance for that proposal distribution, which can be kind of tricky to choose sometimes. So that's a nice thing about Gibbs sampling. The bad thing about Gibbs sampling is sometimes you need to have these conditional distributions be easy to compute, otherwise you can't implement it, right? With Metropolis Hastings, all you had to be able to do was compute the Q and compute the acceptance probability, compute the Q and compute the pi, basically, and sample from Q. So Metropolis Hastings can be done even in cases, well, even quite tricky cases where Gibbs sampling might be impossible. Essentially, you need these conditional distributions in the Gibbs sampling to be tractable, usually analytically tractable, to implement this. So Gibbs sampling is usually, there's usually a subset of problems similar to the EM algorithm, actually, just like the EM algorithm can be used on certain problems where that M step is feasible and tractable. Gibbs sampling is also most useful where these conditional distributions have a nice analytic form, and we'll see some examples where that is true later. Okay.